In this video, we will be determining the formula of compounds knowing the mass of the elements in the compound and percent of each element in the compound. We will be turning in two different kinds of formulas, both the molecular formula and the empirical formula. Empirical is the one that we will actually be able to determine first. So, our first problem. What is the empirical formula of urea if a sample of urea contains 1.12 grams of nitrogen, 0.161 grams of hydrogen, 0.480 grams of carbon, and 0.640 grams of oxygen? So, to set up these calculations, the first thing we need to do in this case, what we're given is grams of each element. So the first thing we should do when we have grams of an element is convert from grams into moles of that element. So let's take the first one here, the first element, nitrogen. I have 1.121 grams nitrogen. To convert to moles, 1 mole of nitrogen, according to the periodic table here, has 14.01 grams nitrogen. So what I find doing this math, 1.121 divided by 14.01, I see that what I have in this case for nitrogen is 0.08001 moles of nitrogen. Doing the same for hydrogen now, 0.161 grams of hydrogen. Convert this now to moles. 1 mole of hydrogen, 1.008 grams of hydrogen, again from the periodic table you see on the right. 0.161 divided by 1.008 gives me 0.160 moles of hydrogen. Carbon, 0.480 grams of carbon. 1 mole of carbon weighs, according to the periodic table there you see, 12.01 grams. So 0.480 divided by 12.01 grams gives me 0.0400 moles of carbon. And finally, oxygen, 0.640 grams of oxygen. Convert to moles. 1 mole of oxygen weighs 16.00 grams. So 0.640 divided by 16 gives me 0.0400 moles of oxygen. And that's great. Now, so that's the first step in this case. We've got moles of each element. Now we need to determine ratios of the moles against each other. And the way we do that is locating the least number in all of these. So what is the least number of moles in all of these? All right. So we see that the least number is really 0.0400, and we see it here in two cases. This is bigger than that. That's bigger than that. So what do? Once we've identified it, we divide all the moles by that least number. So we divide everything by 0.0400 moles. So I divide this by 0.0400 moles. I divide this by 0.0400 moles. I divide this by 0.0400 moles. And this by 0.0400 moles. And so what do I find? In each case I do this math, and this gives me now a ratio of the elements. So 0.08001 divided by 0.0400 gives me 2.00. Sorry for having to write there on top of the periodic table, but you get the point. And that's nitrogen. 0.16 divided by 0.04, I get 4.00. That's hydrogen. And of course, 0.04 divided by 0.04 is 1. So 1.00 carbon and 1.00 oxygen. And this then is my ratio. So what I see is I have 2 nitrogens for 4 hydrogens, for 1 carbon, for 1 oxygen. Now, there are a variety of ways one would write this, typically. All right, you could put them in the order they give them to you here, nitrogen, hydrogen, then carbon, then oxygen. But traditionally what we do is the first element we typically write down in a compound is carbon. So I have 1 carbon. Then the next one is hydrogen. I have 4 hydrogens. The next one could be oxygen or nitrogen. I'm going to do nitrogen next, so N2O. But there's nothing wrong at this level, at least, with just doing it in the order we give it. I haven't given you an order for the elements, so that won't come until organic chemistry. So whatever order you want to put them in, but what you need to make sure of is that you have 2 nitrogens, 4 hydrogens, 1 carbon, and 1 oxygen. All right, so let's move on to our next example. So in our next example, now we have percent of elements. So now we're looking for the empirical formula of nylon 6 when we know it contains 63.68% carbon, 12.38% nitrogen, 9.80% hydrogen, and 14.14% oxygen. Now, in this case, the simplest way of doing these problems, instead of looking at these as percents, all right, in the way that they're written here, what we're going to do is we're going to assume instead of percent that I actually have a 100-gram total sample. And what that allows me to do is convert the percents directly to grams. So if I have a 100-gram total sample and 63.68% of it's carbon, then I have 63.68 grams of carbon in that sample. Now it turns out we're going to divide this effect away, so it's not really going to play any role. It's not going to screw us up. We're going to be fine. And I'll show you how we do that later. So first, 63.68 grams of carbon, 12.38 grams of nitrogen, 9.80 grams of hydrogen, and 14.14 grams of oxygen. Just by changing the percent sign to gram sign, because what we've done is we've assumed, again, a 100-gram total sample. Now I convert to moles, just like in the last problem. So now it's basically exactly like in the last problem. 1 mole of carbon from the periodic table weighs 12.01 grams. And I'll just do all these really quick here. 1 mole nitrogen is 14.01 grams. 1 mole hydrogen is 1.008 grams. And 1 mole oxygen is 16.00 grams. So now I can do all of these individual math steps. So 63.68 divided by 12.01. This gives me 5.302 moles carbon. 12.38 divided by 14.01 gives me 0.8837 moles nitrogen. 9.80 divided by 1.008, that gives me 9.72 moles hydrogen. 14.14 divided by 16 gives me 0.8838 moles of oxygen. Now again, we remember what we're looking for, the least number of moles. And the least number of moles in this case is the nitrogen. 8.8837 is less than all the others. So I divide all of the moles by that. This is effectively getting rid of that fact that we assumed a 100-gram sample. We're sort of dividing that away. All right, so 0.8837 moles is what I'm dividing by in all the cases. 0.8837 moles. 0.8837 moles. 0.8837 moles. And so what do I find for my ratio now? 5.302 divided by 0.8837. So I find 5.999 carbon. 0.8837 divided by 0.8837 is 1, so 1.000 nitrogen. 9.72 divided by 0.8837 gives me 11.0 hydrogens, and 0.8838 divided by 0.8837 gives me 1.000 oxygens. So, putting this all together, remembering my order, or the order doesn't necessarily matter right now because you don't know a proper order from organic chemistry, but what you could report is something similar. You just need the numbers on the elements of C6, H11, NO. And there we have the empirical formula for nylon 6. All right. So, now we're going to take these steps that we've now learned here, and we're going to add one thing to them. And that one thing that we're going to add is how we take that and determine the molecular formula for a compound. So, here we have a problem. And it starts off pretty much the same way as the last problem did. 26.7% phosphorus, 12.1% nitrogen, 61.2% chlorine, and has a molar mass of 580 grams per mole. Great. And we start off doing exactly the same thing with those percents. All right. First, we just report them as grams because we're going to assume a 100-gram total sample, just like before. 26.7 grams phosphorus, 12.1 grams of nitrogen, 61.2 grams of chlorine. And I convert to moles just like I did before. So all this is exactly the same as what I've already done. So 1 mole of phosphorus weighs 30.97 grams from the periodic table. Nitrogen, 1 mole nitrogen weighs 14.01 grams from the periodic table. These are the molar masses, remember. And 1 mole chlorine weighs 35.45 grams. So now I can convert my grams into moles. So 26.7 divided by 30.97 gives me 0.862 moles of phosphorus. 12.1 divided by 14.01 gives me 0.864 moles of nitrogen. 61.2 divided by 35.45 gives me 1.73 moles of chlorine. Once again, we divide by the least number, which in this case is the 0.862 moles. We divide by that, so we divide them all by it. So, divide by 0.862 moles. Divide this, 0.862 moles. Divide this, 0.62 moles. And what do I find? I find, well, 0.862 divided by 0.862 is 1, so I have 1.00 phosphorus. 0.864 divided by 0.862 is 1.00 also. To the significant figures, remember. 1.73 divided by 0.862 gives me 2.01 chlorine, which is close enough to 2. So what do I know? I know my empirical formula is PnCl2. Now, the last bit here is determining the molecular formula from this. Now, because I know this, PnCl2, I can determine the molar mass of that empirical formula. 1 times the mass of phosphorus. So 1 times the mass of phosphorus is 30.97, plus 1 times the mass of nitrogen, 1 times 14.01, plus 2 times the mass of chlorine, 2 times 35.45. I get a molar mass for PnCl2 of 115.88 grams per mole. But what do I know? I know that the actual compound has a molar mass of 580 grams per mole. So what do? I take the known molar mass, 580, don't know why this thing's not letting me do 8 really well right now, grams per mole, and I divide 115.88 grams per mole, and I just get a number. Now, if you've done everything to this point right, this number will be a whole number, or at least close. So 580 divided by 115.88 provides me with, for significant figures, 5.0. Now, what's that tell me? That tells me I have to multiply the subscripts in the empirical formula by 5.0 to get the molecular formula. So in other words, my molecular formula is P5N, 5Cl10. And that then is my molecular formula. All right. So let's do one more example of this. So, maleic acid is composed of 41.39% carbon, 3.47% hydrogen, and the rest of it is oxygen. If 0.129 moles of maleic acid has a mass of 15 grams, what is the molecular formula of maleic acid? Now, the first step is to find again the empirical formula, just like we did before. So, how many grams of carbon if we're assuming a 100-gram total sample? Well, 41.39. So, 41.39 grams of carbon, 3.47 grams of hydrogen, and all we know about oxygen is that the rest of it's oxygen. Well, we know the percent of the whole compound is 100%. If you add up all the percents of all the individual elements, you got to get 100%. So we can find how much oxygen is there by subtraction. So 100 minus 41.39 minus 3.47 tells me that this compound is going to be made up of 55.14% oxygen, or in our case for use, 55.14 grams of oxygen. And now I can convert to moles. 1 mole carbon, 12.01 grams. 1 mole hydrogen, 1.008 grams. 1 mole oxygen, 16.00 grams. And so now I know moles. So 41.39 divided by 12.01 gives me 3.446 moles of carbon. 3.47 divided by 1.008 gives me 3.442 moles of hydrogen. And 55.14 divided by 16.00 gives me 3.446 moles of oxygen. Now, again, we find the smallest number of moles, and that is the hydrogen, 3.442, so we divide everything by that. So divide them all by 3.442 moles. 3.442 moles on the bottom here. 3.442 moles here. and 3.442 moles there. Okay, that's oxygen, by the way. So 3.446 divided by 3.442, that gives me 1.001 carbon. 3.442 divided by 3.442 is 1, so 1.000 hydrogen. And 3.446 divided by 3.442 is again 1.001 oxygen. So our empirical formula here from this is CHO. So now I can find the molar mass of my empirical formula here. 1 carbon, 1 times 12.01, plus 1 hydrogen, 1 times 1.008, plus 1 times oxygen, 16. So I get 29.018 grams per mole as the molar mass of my empirical formula. But now I need to know the actual molar mass of the actual compound. And they give me enough information because they tell me 0.129 moles of it weighs 15 grams. So to find the molar mass, I divide those two numbers. So to find the molar mass of the actual compound, I take 15.0 grams and divide it by how many moles that is. 0.129 moles. And I get 15 divided by 0.129. I get a molar mass, a real molar mass of 116 grams per mole. So that's the actual molar mass. So now I take the actual molar mass, 116 grams per mole, and divide it by the empirical formula's molar mass of 29.018 grams per mole. And so 116 divided by 29.018 gives me 4.00. And so my molecular formula, I multiply all the subscripts in the empirical formula by 4, and I get C4H4O4. And that then is my final molecular formula. So that is the way we approach determining the formula, both empirical and molecular, from percent of each element and from individual grams of each element. And that's always the method you do, and those are always the steps in that order that you always approach them with.